Hey guys, let's take a look at this kinetic question which one of my students forwarded to me. I thought it was quite an interesting case study. Thought we want to have a better look at it. Okay, so the student performed an experiment to investigate a hypothetical reaction. 2k plus L give you M. So the graph of k against time for the experiment is plotted below. So you can see it's a very typical first order kind of graph where we are monitoring your k against time in minutes. Given that the units for the rate constant, right, is this per mole dm cube per minute, which statement is correct? Okay, so one of the first things that you need to notice is that this graph, right, shows that it is a overall first order reaction. Okay, which means that the concentration of K, right, is directly proportional to the rate. Okay, so i.e., if K concentration doubles, your rate also doubles. That's what first order means. Okay, so why did they give us this rate constant, right? I think one of the first thing you need to know is that this rate constant informs you of the overall order of reaction. Okay, so why do they need to tell us this since we already know overall is first order? Because this overall first order may not actually be an actual first order. What do I mean by that? It could be a pseudo first order, pseudo overall first order. Okay, because we have two reactants here, right? We have a K and we have a L. Okay, this graph is telling us K is the only one that's affecting our rate of reaction. But this rate constant tells us something else. This rate constant tells us that the overall order, right, is actually equals to 2. How do I know that is equal to 2? Because here there is a concentration term. Because if you remember, right, your rate equation, let me just write it down. Your rate equation, if it is first order only, right, basically it's just K, your rate equation will look like this. Because it's overall first order, mah. But this is apparently not the case because if you look at the units for the rate constant, right, you actually have one more concentration term left over. If it is just a overall first order, right, a clean first order, a real one, then the concentration term on both sides, I'll denote it using a round bracket, the concentration term on both sides should cancel off nicely. Okay, this is per minute. Which means that your units of rate constant K is always just per time for overall first order, real first order. Okay, but for pseudo first order, what happens is you now have another concentration term on the right hand side, which presumably is your L lah. Okay, so when you bring it over, right, you now have this units because it's an overall second order. Okay, so how do we make this second order to be first order? We have to make L in large excess. Okay, so then this becomes a overall pseudo first order. That's why we can get this first order graph with a constant half-life. Okay, so let's look at the options, shall we? The reaction is elementary. What does elementary means? It means that it is one step, which means that 2K, right? 2 molecules of K and 1 molecule of L, or two moles of K. Oh, sorry, maybe let me write on this side. 2 moles of K will react with 1 mole of L. So 3 molecules are 2K and 1L reacts in one step to get your product M. We all know that that's not true because it is a pseudo first order, right? And if you look at the order, right, of k, it is first order, right? First order. So means that only one. Okay, let me shift my self. Okay, which means that overall pseudo first order, it means that only k, one k, one mole of k is actually reacting in the rate determining step. Rate determining slow step. Okay, so this doesn't tally with your stoichiometric balanced chemical equation. So this is not elementary. Okay, this is definitely not elementary. So option A is out. Okay, let's look at the second option. The tangent of the gradient of tangent at t equal to 0 increases by 4 times when initial concentration of L doubles. Does the This is for like what, second order, right? Second order. If L is second order, concentration double, the rate will quadruple. But we know that that is probably not the case, yeah. So this option is out because L is in excess, yeah. Okay, and overall order is only 2, which means that our rate equation, right, looks something like this, yeah. Rate equals to K, concentration of big K, and concentration of 1L. This is like overall second order. Okay, this is the actual rate equation without making L in large excess. Okay, so L is first order as well. So when concentration double, the rate should double. Okay, rate is equated with your gradient here. Option C, the half-life of the reaction remain constant when catalyst is added. So when you add in a catalyst, you go by an alternative reaction pathway. EA is lowered for both forward and backward. Since both forward and backwards, the rate is increased to the same extent, right? Your equilibrium amounts of both the reactants and product stays the same. So since there's no change in the equilibrium amount, right, the composition, then your half-life will not be affected. It will still remain constant. Okay? So catalyst doesn't affect the half-life being constant. Half-life of this experiment remain constant when K double. This is true because remember your formula here, T half equals to ln 2 over K, the reactant in excess. Okay, so what is actually going to affect your T half is your L. Okay, so when K doubles, nothing will happen to half-life, but when L doubles, your T half will half. Okay, because L doubles, your T half become half mathematically. Okay, so our answer here is D. Okay, that was quite a long explanation, but I hope you got value from it. Remember to subscribe if you got value from it and share this video with your friends who may also need help with this question. See you in the next one. Bye.